Hey there. So for all of you guys taking the Florida Civics test, or anybody who just wants some extra review, I'm posting up this video to help you catch up. So what we're going to be talking about today, this is just going to be the first part of 6.3. We're doing the binomial distribution. So what is binomial distribution? It's kind of similar to like normal distribution in the sense that it is it has its own set of rules, and you can definitely use a part of your calculator to solve the problems. But it has its own criteria that needs to be met, just like normal distribution had like the normal curve that needed to be met with like, the 68, the 95, the 99.7. Binomial has its own stuff that needs to be met. So the first things is the question a binary question? Do we have success or failure, like a yes or no type of question? Okay, that's what we're looking for. The second thing, are the events independent of each other? Are the trials, the outcome of one has nothing to do with the outcome of the other? Do we have, so binary, independent. Do we have a set number? Did they tell us like, oh, out of 10 tries or 250 people are going to do it? So we need a set number. And does every chance, every trial have the same probability? Okay, so the way you can remember these criteria, so it's binomial. See how it starts with B-I-N? It's BINS, B-I-N-S. Okay, so let's do some examples. Genetics say that genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O. Okay, so first we're going to see if it has all these criteria. So is it binary? We have type O or not type O. So that's success and that's failure. So yep, we're good. Independent. Well, it said it wasn't the problem, so we're good to go there. Set number of trials, N, number of trials. It said 5 kids. So N, we're going to use that for number of trials, equals 5. And S, do we have the same probability? Each kid has a probability of 0.25, so we're going to use P for probability. And they all have the same chance of having type O. So this is binomial. B, shuffle a deck of 52 playing cards. Turn over the first 10, one at a time. Record the number of aces you observe. So do we have success and failure? We do. It's ace or not ace. So we have that. Independent. Here's where it gets tricky, because if I got 52 cards and I take the first card, that first one has a 4 out of 52 chance of being an ace. And if it is an ace, the next one has a different chance. 3, because there's one ace now missing, out of 51, because we took away a card. It's affecting my next card's probability if I know that the first one was an ace. So since it's affecting the probability of my card, of my next card being an ace, these are not independent. Okay, so not independent. And one way I'm going to tell you that is because they don't replace the cards. Now, if they had, for example, picked a card and then put it back in the deck, so now you're still starting back out with 52 cards, then that would be independent. But they didn't do that. They took them out. So, whoops, I did not meant to put a check mark. So it's bad. So I don't even need to do the N and the S. I already know my answer is no. All right, C. Shuffle a deck of cards, turn over the top card, put it back in the deck, and shuffle again. Repeat this process until you get an ace. Count the number of cards you had to turn over. All right, so B, we do have a binary. You have ace or not ace. So it is binary. It is independent because they replaced the cards. Independent because they replaced the cards. Okay, and my set number of trials, this is where we get messed up. We don't have a set number of trials. Right? They said just keep going until you get an ace. So you could literally be flipping it the first for 1 card, or you could be flipping it like for 48 cards until all you have left are aces. So this is not a set number, so this is not in binomial. Okay, so binomial distribution is defined by 2 things. So you have n, your number of trials, okay? And you have P, which is your probability of success. So those are the 2 things we definitely need to work with our binomial distributions. So how do you calculate it? So if we were doing that whole kids with type O blood thing, and let's say we just want the probability of exactly one of them, okay, of exactly one of them, so the probability that x equals 1. Okay, so I would do, let's start with this part right here. 1 kid, so the exponent is 1, has type O blood. So I put the probability of type O, so the 0.25, with 1 kid, because only 1 kid has type O. Okay, now I look at who doesn't have type O. If type O is 0.25, not type O is 0.75, and then I have 4 kids who don't have type O. So 0.75 to the power of 4. Now this 5 here is for how many ways to get 1 kid with type O. So it could be the first kid, right? The oldest kid has type O. It could be the second born kid has type O. It could be the middle kid has type O. It could be the 4th kid, or it could be the youngest. Okay, we have 5 different ways to do that. So that's where this this number in front of everything comes from, because there's 5 different ways to get 1 kid with type O. So, don't know about you guys. This formula for how to find how many ways you can do it, it's not fun. Okay, look at this formula. This is how you write it. Okay, it's not a fraction. It's called, like, the way I would say it is n choose k. Okay, the one we just did would be 5 choose 1, because we're choosing 1 kid out of 5. If you don't know what these exclamation marks means, that means factorial. So like 5 factorial would be 5 times 4 times 3 times 2 times 1. You multiply that number with everything underneath it. So yeah, this is kind of an obnoxious formula, not gonna lie. So I'm gonna show you a shortcut. Can't really pull up my calculator right now, but by all means, use your calculator, or I have a link to a calculator on Schoology if you need one for your computer. You're gonna use this function called NCR in your calculator. Okay, this is what you want to be using. All right, in order to access it in your calculator, you need to press the math button. You're gonna move over to where it says probability, right? Like where we used to get rand int or whatever from. And then you're gonna press number 3, which is, looks just like that, NCR. Now, if you have one of the skinny calculators and you type it, you'll be fine. Like it'll show you the blank spots to plug in your numbers. If you have one of my calculators or like a thick one, you're gonna have to press the number first. So you're gonna have to press like the 5 first, do all this math stuff to get NCR on there, and then press the 1. Okay, so in your calculator, it will look like 5 NCR 1. If you have any issues like finding this or figuring it out on your calculator, remind me next time and I'll go over it real quick. Okay. Now, this formula, I'm not going to go too much into because they don't use this in your like test too much. Now, how to actually find the probability formula, this one, okay, it is on your reference sheet. but you do need to know it because I have seen at least one problem of this type, probably more than one, on every practice exam I've seen in the multiple choice. So you should remember this formula, or at least remember where to find it on your reference sheet. It is on the front page in the middle of the box on your front page. Okay, so this is just like what we saw. This is how many ways to get the combination of kids we need. So like 5, choose 1. Your probability of success times how many times you're going to see the success, and your probability of failure times how many times you're going to see those failures. Okay, so for example here, genetics say that children receive from their parents, that genes children receive from their parents are independent from one child to another. For each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose they have 5 children. Find the probability x equals 3. Okay, so probability x equals 3. So I am going to figure out how many ways there are to choose 3 kids out of 5 times, now this is the probability of type O, so there's 3 of those. And the probability of not type O, if 3 have type O, that means 2 don't. So I'm just going to plug that into my calculator. If I plug this into my calculator, it will give me, there's 10 ways to choose 3 kids out of 5. Okay. And I just would type the rest in. Now, you could also type this into the calculator without solving it first. Like, that's fine. And then multiply straight across. However you do it, you do get the answer. Let's see, what do we get? 0.0879. All right, so what does this mean? It says interpret. So there is an 8.8% chance that exactly 3 children have type O blood. Okay. So the next problem says, should the parents, so same scenario, should the parents be surprised if more than 3 kids have type O blood? Okay, so probability that we have more than 3 type O blood. Now, more than 3 out of 5 kids would be 4 kids, or so plus 5 kids. So I'm going to do this again. How many ways can I pick 4 kids out of 5 times the fact that 4 of them are successes with type O and 1 of them is a failure, just kidding, with not type O, plus how many ways to pick 5 kids out of 5 and the fact that all 5 of them have 0.25 have type O. And technically this 0.75, like I have nobody with nothing else. So like you don't have to write that because that would just equal 1. So you don't have to write the next part. All right, so I would just type it exactly like that, plug it straight into my calculator, and we end up with 0.0156. Okay. Should the parents be surprised that more than 3 kids have type O blood? Yes. Okay, since there's only a 1.56, whoop, that 6 came out funny, 1.56% chance of more than 3 children having type O blood. The parent should be surprised. Okay. Now, is there a shortcut to the calculator? Absolutely there is. Okay. Again, you have to like test this out, but on your calculator, when you go to, so this is in second vars. okay, right, where you find normal distribution, so second vars. Scroll all the way down, or even scroll up because it's so far down. It's like options A and B. You have binomial PDF. This binomial PDF, so this is like this example we just did over here. Okay, you would use binomial PDF for that. Because we have an exact amount equals 3. So P is for precise. So we use binomial PDF for an equal sign. Okay, now binomial CDF, C is for cumulative. It has to be this, it has to be that symbol, the less than or equal to. Has to be that symbol. Okay, so a few things. If you have that symbol, awesome. Easy job, right? Probability X is less than or equal to 2. You go into your calculator, second vars, and you choose binomial CDF, and you follow along, you type everything in. So if you have less than or equal to a number, awesome. If you have the probability that X is just less than 10. Okay, we got to rearrange that so that I have a less than or equal to. So if it's less than 10, that means the biggest number that I can have, that it is equal to, is 9. Okay, so now with this symbol, now it matches. So now I can use the binomial CDF in my calculator. Okay, here's where it gets tricky, and this is the one, I'm going to have to go over this for sure when you guys come in class. But when you have a greater than symbol, okay, when you have a greater than symbol, I still need to somehow switch it and make it a less than or equal to. So when you have greater than, okay, so greater than 5, so 3, 4, 5, 6, 7. I need numbers greater than 5, which means I need these numbers, which means I do not want these numbers. So what I'm going to do is, in order to flip it and make it a less than sign, I'm going to do 1 minus those things I don't need. I'm going to do 1 minus the less than or equal to 5 that I don't need. Okay, so I'll do another example. So again, if I have the probability that X is greater than or equal to like 7 or something, so 5, 6, I'm just writing out, I always write out some numbers just so like I am keeping track of what's included and what's not. So I need greater than or equal to 7. I need all these numbers. I don't want these numbers. So because I need to somehow flip this to make it less than or equal to, I'm going to do 1 minus, and then the last number I don't need, I don't want up to 6, that's the number I'm going to be putting in here. I'm definitely going to have to talk about this when I see you guys in person, because this is one of the harder things that doesn't stick in people's heads. Okay, but just be aware, it has to, for your calculator, be less than or equal to. So if we need to manipulate it, right, like to turn this less than into a less than or equal to, okay, we have to. Or turn this greater than into a less than or equal to, we have to manipulate it because your calculator can only do less than or equal to. Okay. But one more time, PDF is for that equal sign. And because it's precise, CDF is the less than or equal to sign because it's cumulative. Okay. So a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, please press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, they must pay the bill. On the first promotion, 250 customers place lunch orders. Find the probability fewer than 10 of them win a free lunch. Okay, so part A, I need to find the probability X is less than 10. So I need to change it to, for my calculator, I need to change it to a less than or equal to. And if 10 is not included, that means the biggest number included is 9. So I'm going to go ahead and do in my calculator binomial CDF because it says less than or equal to. So binomial CDF. All right, your calculator is going to ask you, what is n? What is your number of trials? 250 is my number of trials. Okay, what is my probability to get a number 3 from a deck of cards? There are 4 of them out of 52, and you can write it like that in your calculator, 4/52, that's fine. And then what is my number? My number is 9, so that's the number I'm going to put here. So this is number of trials, probability, and the number I'm stopping at. And just like normal CDF, you do need to label them. Okay, type it in, pause here if you need to. But the answer you guys should get is 0.0061. Okay, now if they said only 9 customers actually want a free lunch, does this result give convincing evidence that the computer program is flawed? Absolutely. This is only supposed to happen like not even 1% of the time. So if that's what happened in real life, like, no, the computer's messed up. So since this only happens 0.6% of the time, there is evidence the computer program is flawed. Okay, like that should not be happening. You should get more than 9 winners out of 250. Okay, so because our probability is so small, we do have evidence that the program is flawed. Okay, now when describing binomial distribution, okay, if the probability is on the low side, so let's say the probability is 0.10, okay, it happens 10% of the time, you would expect to see low numbers, okay? If your probability is high, like it happens 90% of the time, you would expect to see higher numbers. And if your probability is like 50-50, it should look like a pretty symmetric shape, okay? We're gonna go into that more next time, but just keep that in mind. When you have a low probability, you'll see low numbers, high probability, high numbers. 50-50 shot should be kind of in the middle. Okay. Now, to find an average, so like the problem with like the 250 people, okay, if it's supposed to be a 4 out of 52 chance, I should be able to find, like 4 out of 52 is about 7-8%. I should find just 7-8% of 250. So to find the average or the expected number, we are just going to do your number of trials times the probability of winning. Okay, right? So like 250 times 4 out of 52. And you get something like 19. I should have had 19 winners, not 9. Okay, so my standard deviation, spam call. Here's our lovely formula. Both of these formulas can be found in your reference sheet. Again, they're on that front page, just like where you saw that other formula for the binomial distribution. These are right next to it. So you don't have to memorize them, but you do have to know where to find them. So assume each of the 21 students in Mr. Hogarth's AP Stats class who did a bottled water versus tap water activity was just guessing. So there was a 1/3 chance of each student identifying the cup containing bottled water correctly. So this is our probability. That's our chance of getting something correct. Let X equal the number of students who make a correct identification. At the right is a histogram. Oh, I didn't give you the histogram here. Sorry about that. I think I gave it in your notes. Maybe I just don't have it in mine. Anyway, let X equal the number of students who make a correct identification. So calculate and interpret the mean of X. So the mean is supposed to be N times P. So we know P is 1/3. What's N? N is our number of students. So if there's 21 students and I should expect 1/3 of them to get it right, that means my average is going to be 7. This is my average. Okay, for standard deviation, we're going to just plug it into that formula. So standard deviation is the square root. So 21 times the probability of success, 1/3, times the probability of failure, 2/3. And we get something close to like 2.16. Okay. Oh, I didn't interpret these guys. So if all students in class were guessing, and we did this many, many times, we would expect 7 to guess correctly on average. Okay. For this 216, for my standard deviation, if they were just guessing, and they repeated this activity many times, the number who guessed correctly would typically vary by 2.16 from our mean. So if all students guessed, and we did this many times, many, many times, right? Oh, hold on, my handwriting's going funny. Many, many times. The number of correct guesses, or students who guessed correctly, would vary from the mean. By about 2.16. Okay. Let's see. I think that's a pretty good place to stop right now. I will make another video just in case. So this is like those of you who are out on the 18th for the Florida Civics test. If you are out on the 19th, I'll make a different video to help you with that. But this is about where we finished for the day. Okay? If you have any questions, just ask me the next time I see you guys. Other than that, have a good one. I'll see you later.